But we're going to be looking at sound today. And two questions that we could start off with is to think, what is sound and how do we hear it? Of course, sound can be said to be caused by vibrations, and our ears has key features such as the eardrum or the ossicles, which includes the hammer, the anvil, and the stirrup that allows us to hear. Now, apart from that, how else can we detect sound besides hearing it? Of course, we can feel sound. Some deaf people can feel their eardrums vibrate in response to a loud sound even though they cannot hear the sound. Sound can also be detected electronically by a microphone and visualized as waveforms. Now let's think about this. Sound travels as vibrations between air particles. The pinna funnels sound into the ear canal, and the sound makes the eardrum vibrate, which then makes the ossicle, these tiny bones, vibrate as well. The cochlea converts the vibration into electrical impulses, and of course, the auditory nerve carries the impulses to the brain. To make sound, an object must vibrate. For example, a guitar string, or vocal cords, and ridges on a male grasshopper's hind leg. Now, the object vibrates, and as we can see, this makes the air particles vibrate. So the vibrations are passed through the air, and as such, the vibration will then reach our ears. Now, we can detect and visualize sound. Now, we have said previously that hearing is basically your brain making sense of how hard and how fast your eardrum vibrates. We can also use a microphone and oscilloscope to detect vibrations, such as for that of sound, and turn them into electrical signals. Now, oscilloscopes display sound as transverse waveforms, but sound waves do not really look like this, but they are much easier to visualize in this form. Now let's think about amplitude and volume. The question here says, which of these sounds would be louder? Now, as we pay attention to them, A and B, we can thus deduce that sound B is louder than sound A, because if you look at the height, B has 2 centimeters in height compared to A, which has 1 centimeters. So wave B has a greater height, meaning larger vibrations. Wave height is called amplitude, as we all should be familiar with. Now, the higher amplitude is equal to bigger vibrations, which of course means higher volume. What about frequency and pitch? Now, which of these sound has a higher pitch? Let's see. Sound Y is higher pitch than X. Why? Well, Y has more complete waves or vibrations per second, and we know that frequency speaks about the number of waves passing a point per second, and Y fits this. So if we look, X has 1.5 wave cycles and Y has 3 wave cycles. So it is confirmed. Now, the number of waves per second, as always, is frequency. And if we have higher frequency, that means faster vibrations and therefore a higher pitch. Let's look at this simple recall. An oscilloscope allows us to see the vibration of sound as transverse waveforms. And as you increase the amplitude, the height of a sound wave, the vibration gets bigger, and you increase the volume. As you increase the frequency of a sound wave, the vibration gets faster, and you increase the pitch. Okay? Now, when we're making sounds, we have to now think about how can we recall what is meant by amplitude and frequency of a waveform. And we should be able to describe how amplitude and the frequency of wave relate to the volume and pitch. I hope those questions would have been answered previously. Now, we can also interpret oscilloscope data and draw waveforms of different volume and pitch, and it's something that we can practice. Now, let's think about this. You can try this. For the first one, we notice that it's quiet, low, and lower pitch. So if we look at the next, it's quiet and higher pitch. And in this instance, it has a greater number of waves, right? So of course, it's going to be higher frequency, higher pitch. When we think about louder and lower pitch, so it's same amount of frequency, but it has a higher height or higher amplitude. So we can observe what we see there. And of course, louder and higher pitched, well, still has a high amplitude, but also numerous waves, which makes it high pitched. Now, having gone through drawing waveforms and looking at volume and pitch and amplitude and frequency, we are now going to interpret oscilloscope data and draw waveforms of different volume and pitch is one key thing that we have been trying to do. And of course, describing how amplitude and frequency of wave relate to the volume and pitch of sound are some a key thing as well. We have also recalled what is meant by amplitude and the frequency of waveform. So let us give ourselves some practice. Now the diagram below shows a pattern produced on an oscilloscope by 3 different sound waves. Now the question asks, which 2 waves have the same loudness? And we are supposed to write the letters. And of course here we have A and C. If we were to measure the height, we recognize that they are the same. And how is it that we know? Well, their amplitude are the same. Now, to move further on, it says which 2 waves have the same pitch. And of course, when we look at the diagrams, we can recognize that B and C have the same pitch. And of course, we know this because their frequencies are the same, and we can count how many waves are there. Now, Shuli is listening to a sound that produces the pattern below. Describe how the sound that Shuli hears changes between X and Y. What we can tell you is that the pitch becomes higher. As you'll notice, in the early parts, the frequency is lower, and afterwards, it has greater frequency. So the pitch is becoming higher. Now, diagrams A to F show waveforms for 6 sounds. The waveforms were produced using an oscilloscope. Use the diagrams to answer the questions below. Now, the first question is, which sound has the highest volume, which is loudest, and which has the lowest volume, which is quietest? Now, it's quite obvious that the highest is B and the lowest is C. Clearly, because B has the highest amplitude. Now, question 2 says, which sound has the highest pitch and which is the lowest pitch? Now, the highest is E and the lowest is F. Clearly, this is because E has the highest frequency, which is about 3.5 complete wave cycles, and F is the lowest frequency because it has not quite 1 full wave cycle compared with 1 complete cycle in B and C. Now, which sounds have the same volume? We're having A, D, and E because F is slightly quieter. And for 4, which sound has the same pitch? We have B and C. As we know, F is slightly lower pitched. You may be wondering, why does F has the lowest frequency? Now the waveform finishes at the blue arrow. To complete a full wave cycle, it would need to reach the red dotted line. Now, of course, F has a lower volume than A, D, and E because the vertical arrows do not quite cover 4 full squares. So the amplitude for F must be less than 2 centimeters. Now, another thing that we are going to look at is wave speed. Interestingly, it's a very straightforward concept. Wave speed is equal to the frequency times the wavelength. And I normally start off with doing the symbol in the triangle, and then I would look at different parts. So I know that V here is representing wave speed, and its unit is meters per second. F here represents frequency, and the unit is hertz, followed by the wavelength, which is shown here by the lambda, and the unit is in meters. And of course, we can always find the alternative forms by simply covering up what we want to find. So if we cover V, we have F times lambda. If we want F, we cover F and we're left with V divided by lambda. And then finally, if we want lambda, we will cover it up and we're left with v divided by f. Very straightforward and very direct. All you have to do is just know the triangle and what each part means, and of course, what the correct unit is. Now let's look at this past paper question. In part for the one that was on your exam. Now it says calculate the speed of a sound wave with a frequency of 250 hertz. Highlight that. And a wavelength of 1.3 meters. You highlight as well. We now need to think about what is the equation we're going to use. We're going to use V is equal to F times lambda. All right, where V is the wave speed, F is the frequency, and lambda is the wavelength. Now let's substitute the value. So it's 250 hertz times 1.3 meters, which will end with 325 meters per second. And remember, the unit is very important. Now let us move to the next question. This question is asking us to look at the diagram that shows the oscilloscope trace of two different sounds, P and Q. The oscilloscope setting is exactly the same in both cases, so P and Q sound different. Now, what you would realize is that we have one wave, there's 2.5 in terms of complete cycles. And for the second, we have 1, 2, 3, 4, 5. 5 complete cycles. So if we think about it, Q is equal to 2 of P in terms of cycle. So that could give you 1 mark there. Now let's think about this. Q is louder because it has a bigger amplitude. All right? And Q has a higher pitch because it has a higher frequency. And you could say Q has twice the frequency of P, and that's 5 marks there. So whenever you get into the exam, you have to be careful. Look at exactly what is provided and note what is given. This will allow you to pick up your marks and look what they're asking you for. Write down 2 different ways in which they sound. You're looking for 5 marks, right? So you get 1 mark here, another mark for explaining, another mark here, another mark for explaining. And you have 4 marks there. Now you need that total 5 mark. You have to make a comparison between the frequency of each. And you could also note that the amplitude as well is also 2 times that value.